All right, this is video 3 for the mechanics unit notes. With this one, we're going to start talking about dynamics. Now, this is the study of forces acting on an object. Now, a force is simply a push or a pull. So what that means is that forces have direction, like velocity and acceleration, and that makes a force a vector as well. So what are some different types of forces out there? Well, we have gravitational forces. We have tension forces. Tension force would be forces in ropes, strings, cables, things like that. We have elastic forces. So rubber bands, springs, things like that. And we can think of even more. So those are just 3 examples, but there are more out there. So when we study all of the forces acting on something, we call that the net force. And there's a relationship. The net force equals mass times acceleration. And the way I like to write it is with a sigma symbol. So something like that. So what that means is that the units for force, if we look at it, we see that the Newton equals a kilogram times a meter per second squared, or meter per second per second. Collectively, we call this Newton's second law, but that's not so important. We just want to be able to know how to use it. So notice that if I have a constant net force on 2 objects, the object with the least amount of mass would get the greatest acceleration, and the object with larger mass would see a small acceleration. And that's very important. The motors we use in robotics can only exert a certain amount of force. That's pretty much constant. So the more mass you add to it, the slower the acceleration. That doesn't mean that they can't get fast. That just means that it takes them a longer time to build up their velocity. So what if acceleration were 0? Well, if acceleration were 0, we would say the forces would be balanced. I have that in the wrong area. So if the forces are balanced, that means that if I have an object, and if I have 5 newtons pushing one way, 5 newtons pushing that way, the forces would be balanced. They would cancel each other out, and the acceleration would be 0. That means the object would either be at rest, or the object is in motion. If it is in motion, it has to maintain the same speed and direction. That's important. If the forces are unbalanced, so let's say this is 5 newtons, this is 3 newtons, they do not cancel out. Well, then we do have an acceleration. And the net force divided by the mass would equal the acceleration. So the acceleration would be directly proportional to the net force and inversely proportional to the mass. So this is all linear force. We do have something called rotational force. That's called torque. Torque is how much force is needed to rotate something. So let's say I have this wrench here, and I have a force A and a force B. Which one would lead to the greater torque? And I think we can all agree that it's going to be force B. So what torque is, the way we calculate it is it's a force times a lever arm distance. But we have to be careful. Notice that a force pulling in this direction would not rotate that wrench, or a force pointing in this rotation will not turn that wrench. This force must be perpendicular to the lever arm distance in order for it to create a torque. That's very, very important. So this means that we're going to have to do just a little bit of trigonometry. So here we have this red bar, and we want to rotate it to right here. And we see that we have this force being applied. And this force is being applied at some angle theta. Well, this force can be broken up into an x and a y component, or a parallel component and a perpendicular component. Notice that the parallel component does not help to rotate this bar, only the perpendicular one. So we need to calculate that. Well, there's a rule about vectors which says once you draw a vector, as long as you keep its length the same and its arrow pointing the same direction, you can move it wherever you want to. So I can move this vector right here, putting it opposite of that angle. So I see that this perpendicular component would equal this force times the sine of theta. So to get this torque then, it'd be that lever arm times force times sine of theta. Sometimes you have to use cosine. What's important is that the force must be perpendicular to the lever arm. All right, now load. We define load as an external torque that we apply to a motor. That's going to be very important when we talk about the DC motors and how torque and load affects them. So whenever you hear the word load, just understand that I am meaning a torque. All right, now we can also study torque as it relates to the rotational motion of an object. So remember, for the linear, we had the net force equals mass times acceleration. We have the same thing for rotational. The net torque equals I times alpha. All right, now I. This is something new. It's called the moment of inertia, and it measures how much something resists to being rotated. And it depends upon the object's geometry. So for instance, if I have a solid sphere, its moment of inertia would be I equals 2/5 mr squared. If I have a ring, this would be kind of like a wheel, I equals mr squared. And then if I have a disk, like a solid disk, I equals 1/2 mr squared. All right, now if I have a uniform rod and I wish to rotate it around its center, I would equal 1/12 ml squared. If I took that same rod and tried to rotate it around its end, it'd be 1/3 ml squared. So notice it's harder to rotate this rod around its very end than it is to rotate it at its middle. And I think we can all experience that. Now let's say the object is slightly different than what we see. We can calculate its moment of inertia using something called the parallel axis theorem. So let's say that I wanted to calculate the moment of inertia for a rod at its end. So the axle is right here. Well, to do that, the moment of inertia would equal the moment of inertia at its center of mass. Well, for a rod, that's 1/12 ml squared plus m. Now, d is the distance from where you're trying to rotate it to its center of mass. So for this, it would be L/2. We'd want to square that. So that would equal 1/12 plus m. This would be L squared over 4. So I could rewrite this actually to be 1/4 ml squared. 1/12 plus 1/4 is 1/3. And that's what we had written above. So this is the parallel axis theorem, and we could try to find what the moment of inertia is if we rotated it at this point. We could do that. We just have to know what d is. All right, energy and power. Work is how much energy is needed to move something. So work, which we measure with the joule, energy is always measured in the joules. Work equals a force times a distance, but this force must be parallel to the distance. So in this diagram up here, that's why this work equals this force times cosine of theta times the distance, because we'd have to use the cosine function to get that parallel component. But work is always a parallel force times the distance. Another formula for work is the work kinetic energy theorem, where work equals the change in kinetic energy. Kinetic energy is 1/2 mv squared. So what we can do is we can take a look at the final kinetic energy minus the initial kinetic energy, and we can calculate how much work is being done. So that'd be like calculating how much work is needed to accelerate a car from, let's say, 10 miles per hour up to 100 miles per hour. Power. Power is work divided by time. It's how much energy something uses per unit time. We've probably seen its unit is the watts. So we've probably seen power most often in light bulbs. Let's say we have a 100-watt light bulb. That means it's converting 100 joules of electrical energy into 100 joules of heat and light energy every second. That's what the 100 watts means. Now we can also use power in electrical circuitry, and I'll let you study this engineer's wheel here for volts, amps, ohms, and watts. And there's a lot of really good formulas with that. All right, that concludes this video for this part of the notes.